Hello. In this video, I would like to share with you ways to compute confidence intervals, which are used to estimate the true value of a population parameter. Confidence intervals are important for us because sometimes it's just not possible to compute the actual mean of a statistic among a population. For example, there might be 20,000 licensed drivers that pass a speed trap in each day. Three samples were taken, and in one, 5% of the drivers admitted to having received a speeding ticket here before. Another sample showed 10%, and another showed 15%. The true population mean is somewhere along this scale, and we would like to state with some level of certainty whether the true mean exists close to any of our samples. To compute a confidence interval, you must follow these steps. Step 1. Verify the requirements. There are three requirements. First, the sample must be a simple random sample. That is, that it is an unbiased sample. Second, the population must follow a binomial distribution, which has the following requirements that were discussed in another lesson. And third, the sample size must be greater than 10. After verifying the requirements, step 2 tells us to use the area under a standard normal curve table to find the appropriate critical value that corresponds to the desired confidence level. Popular confidence levels and critical values are as follows. At 90%, or a 90% confidence level, a critical value of a z-score would be 1.645. At a 95% confidence level, a critical value or z-score would be 1.96. At a 99% confidence level, a critical value or z-score would be 2.575. I will show you how to obtain these critical values in just a moment. The third step requires us to evaluate the margin of error using this formula. The critical value times the square root of the sample proportion of success times the sample proportion of failure divided by the sample size. Finally, in step 4, use this margin of error to compute the confidence interval. The confidence interval is simply the sample statistic plus and minus the margin of error. Let's revisit step 2 for a moment. In a standard normal curve, a 90% confidence interval correlates to an area under the curve between two endpoints that is equal to 0.9. This means the area outside of the boundary, alpha, is equal to 0.1, which also means that half of alpha is below the left tail and half of alpha is below the right tail. We will use our table to find an area of 0.0500 This would provide us the z-score necessary to obtain this position. The area 0.0500 does not appear precisely in this table, but it does appear between 1.64 and 1.65. So we can call it 1.645. The sign in front doesn't really matter because the area under the tail to the right side would correlate to the same z-score to the right of center. Let me demonstrate an example. Within a survey of 1,200 drivers, 300 have admitted to receiving a speeding ticket. We must find the margin of error for the 95% confidence interval used to estimate the population proportion. We've already discussed this scenario earlier in the video, and the requirements have been met. The confidence level is provided, and the areas under a normal curve table look like this. Alpha is 0.05, so alpha divided by 2 is 0.0250. And we need to find it in the areas under a normal curve table. Here it is at a z-score of 1.96. The probability of success in this sample, or p hat, was 300 out of 1,200, or 0.25. Therefore, the probability of failure is 1 minus p hat, or 0.75, 75%. Our sample size was 1,200, so we now have enough information to compute E. Using a calculator off screen, I get the result of 0.0245, or 2.45%. Please try to compute the margin of error for the 99% confidence interval on your own. Pause the video now and resume playback in a moment to check your work. The margin of error this time is 0.0322 when rounded. Now we can use the margins of error to determine the confidence intervals and describe what it means. For part A, the sample proportion, 0.25, minus the margin of error is 0.2255. And the sample proportion plus the margin of error is 0.2745. So we would say with 95% confidence, the true population mean is between 22.55% and 27.45%. To increase our confidence to 99%, what would happen to our interval? Confirm your suspicion by completing Part B of this question now. The interval grew. With 99% confidence, the true population mean is between 21.78% and 28.22% of the drivers having a speeding ticket. Please try the last example on your own. Notice the 98% confidence interval is not one of our common intervals, so you must look it up in the area table. Also remember that you must compute the margin of error before you can compute the confidence interval for this scenario. Pause the video now and resume playback in a moment to check your work.